Hello, everyone. So here I am discussing what's called the alternating series estimation theorem. This theorem is used to approximate the sum of alternating series. Now, normally we don't have a formula for every series that exists to find the sum of it, such as in the case of geometric series, which we know it converges when the common ratio, the absolute value of it is less than 1. We know that that series, geometric series, has a convergent form, and we can calculate it using the formula that we've seen. But now, particularly, we're going to focus on alternating series. And we know what alternating series look like. They look like this kind of series where you can separately say that there is a sequence B sub n. And all we're doing to B sub n, the sequence B sub n, is we're tagging along a negative one or positive one. And usually it starts with a positive B1 term and then a negative B2 term, and then you're adding a positive B3 term and then subtracting a B sub 4 term. And it just alternates as you continue along the series. So supposing that we have a alternating series whose terms are non-increasing, meaning that it usually either stays the same or decreases. That's what this means by saying that B sub n plus 1, the next term is either equal to or less than the previous term. And if the limit of said sequence goes to 0, then we know it's convergent, right? We know it converges. So that's something that we can say here. We know from here that the series negative 1 to the n minus 1 b sub n converges. And it converges to a sum called S. Now, we're not so concerned about whether or not it converges. We're assuming that we have alternating series that do converge, and it converges to some value, and we call that S. Now, what we're concerned about in this theorem is that there's a certain remainder, or called an error. They're synonymous in this context. There's an error between the alternating series and what it equals, the sum of it, right? The actual sum, which is what happens when you take all the terms infinitely many and you add them all up and you get a certain number at the end because we're assuming that it converges. So given the converging value S, we also can estimate the converging value with a partial sum, which is finding the first n terms of the series. And that would give us a close approximation to the actual term. And we're saying that that remainder between, the remainder is defined as the difference between the actual, this is the actual sum, and C sub n, S sub n is the partial sum. So if this gives us an approximated value, right? This is an approximate value. And this is an exact actual value. If we subtract these two sums, we would get some kind of remainder. Now, the thing is, we don't always know what the actual sum would be, but we can always calculate the partial sum because it's a finite number of terms. Whereas the actual sum is an infinite number of terms, and it gets more complex as the sequences get more complex as to how to find the actual sum. But regardless, this could be known or unknown, but we can find this no problem because we have the computational power to do so. Now, the real thing is we're trying to bound. We're trying to see how bad the error or the remainder can be. What's the bound of this said error? And the bound is simply the subsequent term in the sequence. So if you stop at the first n, so if I stop at the first 3, right? If I add B1, B2, B3 together, this is the partial sum of the first 3 terms. Then what would happen is, according to this theorem, then the error made by subtracting the actual sum from the partial sum that I just discussed right now, just like a simple example, then that's going to be bounded by B sub 4, whatever B sub 4 is. So B sub 4 is the bound. This becomes the bound to the remainder produced by the partial sum of the first three terms. And I know that sounds like it's a whole lot, but hopefully the next example here can explain a bit what we're talking about. So here we have a series alternating. Okay. And we want to find, pardon me, we want to find the sum of the series and approximate it to the accurately to 4 decimal places. Now, this is going to be very common, this terminology of either approximating to 4 decimal places, 3 decimal places, 5 decimal places, 6 decimal places. This number here can be any number you choose. 4, 5, 6 is very common. Now, if you want to have a sum that is approximately correct to the nearest 4 decimal places, this immediately concludes that the remainder, whatever that may be, must be bounded or must be less than an error of 0.00001, or in other words, 10 to the negative 5 power. Because I want the difference of the first 4 digits to be 0. I don't want there to be a difference between the first 4 digits of the actual sum with the first 4 digits of the partial sum. Okay? So that's the conclusion we make based upon what we're given to find. So again, I want to find the sum of the series so that it's accurate to the 4 decimal places, which means that if you subtract the actual sum, if I were to subtract the actual sum of the series with the partial sum, whichever that may be, then I would be accurate in the first 4 decimal places. So that means that this error, the error must be at most, or it must be less than some value being less than 0.001. That's the way we would start. Okay, so with this in mind, now let's just unfurl the sum a bit. So this is really about just writing out a few terms, first few terms of the sequence of the series. So when n equals 1, what's my series look like? It looks like 1 over 10. And that's according to this expression here. Now, when n equals 2, then I have a -1, right? Because -1 to the 1 power is -1. Then I have a 2 squared, and I have a 10 to the 2nd power. When n equals 3, I'm going to add 3 to the 2nd power over 10 cubed. When n equals 4, I'm going to alternate with negative. I get 4 squared over 10 to the 4th. When I have next one, the next term, n equals 5. And this is 5 squared over 10 to the 5th. When n equals 6, I get 6 squared over 10 to the 6th plus minus plus minus, right? So then this is going to be my first term, b sub 1. This is my second term, b sub 2. This is my third term, b sub 3. Fourth term, b sub 4. Fifth term, b sub 5. Sixth term, b sub 6. Now, what I want to do, though, is now have a decimal representation of these numbers, because it helps us understand what the remainder should be. So b sub 1 is 0.1. B sub 2 is 4 out of 100, which is 0.04. B sub 3 is 9 out of 1,000, which is 0.009. So you start to see a little bit clearer, right, what the values are. And then you got 25 over 10. Sorry, I skipped one. You get 16 over 10,000, which should be 0.00016. And then b sub 5 is 25 over 100,000. This would be 0.000025. And yeah, okay. And then last one, b sub 6 would be 36 over 1,000,000. And let me just this is a good time to use your calculator. So I will share my screen. I am sharing my screen, but I'm gonna share my calculator screen with you, right? Just to make sure, sometimes the values are a little bit off. Let me do it by hand all the time. So this is exactly 0.016. So yeah, I've included a bit more. I had a feeling I did it a little too quickly in my head. So that's 0.016 and then 25 over 10 to the 5th should be 2.5. So it's going to be 2.5 10 to the negative 4. So you're going to have 3 zeros instead. This is 25. And then lastly, B6, that's going to be 6 divided by, 36 divided by 10 to the 6. And again, this is, going back to mathematics done in elementary school, middle school, where you move the decimal point to your left, right? And you get, the point is, I want a number. The point is now I have a number that I have a number here where the first 4 digits are 0. Eventually, b to the 7 will have 5 zeros, right? But I don't need that because all I need is for the first 4 decimal places to be zeros for the remainder or for the error. So what this means is by the alternating series theorem, I should say alternating estimation theorem, by the alternating estimation theorem, R sub 5, which is equal to the difference between the actual sum of the series minus the first 5 terms of the sum, S sub 5, the partial sum. This is bounded by B sub 6, which is 3.6 times 10 to the negative 5 power, or in other words, 0.000036. This is telling me that if I calculate the first 5 terms of my series, then the difference between that approximation of the series to the actual series, that difference is accurate for the first 4 decimal places. That's what we're trying to figure out. So in this case, so we would say this. So from this conclusion, we would say that the actual sum of series S, the actual sum of the series S, and the partial sum S sub 5 is accurate, is correct, or are the same, are both the same for the first 4 decimal places. That's the conclusion I am making according to the alternating estimation theorem. So all that I really can say now is that the actual sum is approximately the first 5 digits, obviously the first 5 terms of the series, which just entails for me to add b sub 1 minus b sub 2 plus b sub 3 minus b sub 4 plus b sub 5. This would be accurate, whatever these numbers would be, which is going to be 0.1 plus 0.04, sorry, minus, plus 0.009 minus 0.0016, and then plus 0.00025. If I add these numbers, I should get the sum of an approximation that is accurate to the first 4 decimal places for the actual sum. So now all that it takes is to actually add this up. So let's add this up. I'll share my calculator here. So I'm going to add, I'm just going to add them as if they were actual fractions. I got 1 over 10. That's my first term. Then I'm subtracting that with 4 over 100. Then I'm adding that to 9 over 1,000. Then I'm subtracting that by 16 over 10,000. Then I am adding that, pardon me, to 25 over 100,000. When I answer that, I get the value 0.06765. See that? Let me just switch that real quick. So for the first 4 decimal places, I know that this sum is accurate to the actual sum. So the first 4 decimal places are accurate. And I stop here.